All right. All right. So welcome back. Welcome back to this channel. In the last video, we have understand and derived the theoretical intuition of like variational autoencoder. What is a variational autoencoder and all that. In this video, we are going to do like a quick project. We are going to just do a quick project on like using this variational autoencoder. We'll be developing a variational autoencoder from scratch and use like use it for solving a music problem, the exact music problem that we have described earlier in the last video. We have in the last part I have described the like a project by TensorFlow or Google, in which they have used like variational encoder to actually merge musics, right? So we are going to build a similar model like that. We're just going to generate new images, it's new data, but rather than just using images, right, we are going to now do it for music. So it is going to be dot one. So we are going to use this data set. The data set is actually called GTZan. Uh, I have actually used this data set for audio classification. So like the main thing they have created this data for is to actually uh, enable people to build to train like audio classification models, or I'm just going to show you how the data looks like. So the data contains these directories, and then the main directory that we actually care about is this genres original genres original, in which there are like bunch of classes of music, right? We have like different classes of music. So we're gonna have like different classes of music, right? So we're gonna have different classes of music, in which each class is going to have 100 music or like audio data, and we are going to, our goal is to actually build a model to to classify these images. At least it used to be when they build the model, but we are going to use the same data set for a different problem, for a problem of generating new music. So let's see. All right. So this is the notebook. I'll put this notebook in the description. Here now I'm running it. I'll run this in Kaggle, using Kaggle. I'll not run it in Colab separately, because we have to download the data. The data is about uh 1 GB. You could download it again if you want to, but I'm going to run it on Kaggle. Just use the internal storage to actually store it and use it. So yeah, let's just go through the code first, and then maybe run it again. Right. So first we're going to install TensorFlow docs, right? And then I'm going to install a bunch of libraries here in the second cell. I'm going to install Librosa for performing some audio pre-processing, right? And then we're going to import NumPy. I will import pandas and OS to actually work with the data. I will import TensorFlow and TensorFlow add-ons for extra functionalities, and also will import TensorFlow.keras.layers. We'll also import TensorFlow or matplotlib.pyplot, like to actually plot this maybe the training accuracies, right? And then, or even plotting like the diagrams that will be generating from the audio. And we are going to import like IPython display to actually display the audio in the in this cell or in this environment. I'm also going to clear output, right? I'm going to import like bunch of this, and then after that you can actually start the session, just to make sure that no matter how many times you run this, you get the same values when you're running the random function. We'll set a seed, right? That is what setting seed means. And then we'll define the training size. What is the training size? So the training size is going to be like 60,000. The batch size is going to be 10. The test size is going to be 10,000, and the number of epochs that will training the model is 5. Of course, you could increase the epochs if you want to have like better results. Of course, we are not going to have any good results, I'm telling you. And then number of examples generate and all that. So this is the base path, the base directory that contains all the data that we want. Again, as I've told you, in this Zan, we should go to this folder which contains all of this audio data. Right? I'll specify that. I'll create a function in which I'll just create a music list. I'll take in the class, whatever the class the user wanted me to, or whatever the class on which we'll call this function, right? We're going to call this class. right? And then we're going to like create a music list in which we just get the os dot lister of like we'll just get all of these values, like all of the audio data. We have 100 we audio files, right? We'll just get all of them, and out of these 100 files we're just going to randomly pick like, we are just going to randomly pick some audio files, because we don't want to train the model on like all the data, because we are building a variational autoencoder and it might take like huge complexity. So therefore, we are not going to train the model on like all the data. And again, we have to do this for like all the classes. So that is definitely a problem. Will not be going to do that doing that. So therefore, we just get some images and we are just going to create a list that contains all of the names or the parts of all of these audio files, the selected audio files, right? And then I'm going to create this load function, right? Which I'll take the file. I'll just load this file into like something called librosa to actually convert this into like a something uh like numerical representation form. If you think about it, audio cannot be represented in terms of numbers, but it can be represented with features, especially for the use of machine learning or even audio representation. uh, we'll be learning about how to represent audio maybe in the future section, where we'll actually learn about audio working with audio or generating audio or something, right? So we're going to load the file, right? With some of the parameters like duration and all that, and we'll reshape this into this vector, essentially, yeah, vector. And then we'll just return this data, and then we'll just um we'll just create a function in which you're going to take this file name. We are going to like pass that through we're just going to create a function. So essentially what we'll be doing is we'll be applying this load function to all of the file names. So yeah, and then we'll be loading this data on this like jazz files, right? In this class we have like jazz class, a separate class, and so we're going to train the model on this class. I'm going to call that data set loader on this class, and then we can just load the values, right? If I just run it, actually listen to it maybe. Yeah, so that is like one element of this. And you could definitely change these values and to actually like listen to like all of them, maybe, or specific set of them. And now you could actually, as we have converted this like audio into like image format or numerical format, we could actually visualize these values, like all will be numerical formats, right? We can actually like see all of these values. So we here have like, I think, yeah, we have like four audio, so you can actually see the time series, right? Just like it's time series. All right. So now let's like create TensorFlow dataset. Right, we'll just call TensorFlow dataset on like track set 1 and track set 2, right? And then we're going to map, and then we're going to map this function to this function that we have just created here, map data function. We're going to map this function to all these values of like track set. We're going to shuffle this and also create batches for batch wise training. And we're going to do that same for test data set, but now with track set 2, right? So that is for like pre-processing. That I think that's it for pre-processing. Now let's look at model building. How can we actually develop the model? So we'll be developing like ResNet 1D block, right? So we're going to have like, this is the encoder layer and this is the decoder layer, right? So as you can see here, yeah. So we'll be having like we'll be taking kernel size, filters, and type, whether you want to build like encoder and decoder, or no, yeah. And then we're going to create this for encoder, in which we'll be having 1D convolutions of like these many filters, these many kernel size, two stride and padding to be same. We're going to have two layers, and then we are going to perform instance normalization, right? We're going to have two layers of instance normalization, and then the decoder, right? So we're going to have many convolution 2D, convolution 1D transpose layers. And again, as if you can observe here, we don't use convolution 2D transpose or convolution 2D, because we are only dealing with one-dimensional data. We are not dealing with images, right? We are only dealing with audio data. So therefore, we'll be only needing 1D. right? And then we're going to perform batch normalization, and this we'll just return like one block. So this is just one block, and we could use many of these blocks as you want. And the call function, like main function, will be taking the input tensor, right? And then we'll be passing that to like a ReLU of, and then we'll be performing con 1a. So essentially, yeah, so we'll be performing all of these layers. We'll be performing con 1a. So if like when you want to create a resonate block, no matter what that is, for the encoder and decoder, we build the same function or same class, and you can just call this with different names or different types, right? And then if it is encoder, we'll be using this function, and if it is decoder, we'll be using this function, and so on. So we'll be having like right. So we'll be having like many of these layers. So we'll be performing conventional 1a, either this or this, based on the input of this input when we actually call this function. Okay. So yeah, so we will be having bunch of these conventional layers, and then I'm going to perform normalization. The first normalization layer, and we'll be performing leaky ReLU, and then and then we'll be performing like the second conventional layer, the normalization and leaky ReLU. And then we'll be having, as you're talking about residual connections, we are going to create, we're going to add this input tensor, whatever that is, to this X or to the output, just to solve the problem of vanishing gradient again. And then we'll be performing the final ReLU and returning this X. So this is like one block. So when you are building the main model, we can just use these blocks, many of these blocks, and call them with different like parameters, either either for the encoder or the decoder, and we'll actually build the model. So that is the idea. Now let's build this main class, the main class through which we will build the actual model that we want to work with, right? So the model name is CVAE, convolutional variational encoder, right? In which we're going to take in the latent dimension as the input, right? I'm going to specify the self.encoder first. We'll be creating the encoder, and then I'm going to create a sequential class with the input layer, right? We'll be having the first kind of convolutional 1D block, and then we'll be calling this class resonate 1D block, and we'll be having like number of kernels and all that, and we're having another conventional 1D block and then another resonate block, and just we are just going to increase the like the number of layers, because I mean we have to, because the data is like audio data, and it might be pretty hard, like not that like that for images. So generating music is relatively harder problem. So therefore we'll be having like many layers, resonate 1D block, conventional 2D and 1D, and resonate 1D. And then we'll be performing flatten layer. So we'll be flattening all of these outputs. So all the final convolution layers outputs also will be just flatten them into single dimensional vector and pass them through dense layer with latent dimension plus latent dimension. Again, I have explained why this is, rather than just putting latent dimension, why we have like 2 into latent dimension size, because we want to get like mean and variance, right? And we'll create the decoder now. We'll create the same sequential we'll call the same sequential method. We'll pass in this list that is a model. So we'll be having like input layer, reshape layer, and then now again we are going to call the same resonate 1D block, that we have used here, but with decode parameter, just to tell it that we are building a decoder now. So therefore we are going to run this set of functions, or we're going to have this set of layers, convolutional 1D transpose layers. We'll be performing them. We're going to have another convolutional 1D transpose, and bunch of combinations of that, right? And you can actually see how like the kernels are decreasing over time, like slowly converging, right? You can see the almost same pattern here also. So and then in the final layer, we're going to have this output, because if you can remember, the output of our model is actually this. What? Wait a minute. Yeah. So the output of our model is 900,000 or 9,000. Yeah, 900,001 by 1. And then we are making sure that we generate the same shape. So therefore, we are having this shape, right? And then That's it for the architectures. Now let's build the sample function, right? Same as past. If epsilon equals none, if we don't input anything, we'll be creating a random array, which is of the self latent dimension. We're going to call the encode function on this epsilon, and then we'll build the encode function with which calculates mean and log var. We are going to pass that through. We're going to pass this x, the input audio, right, into the self dot encoder. We will pass that through the encoder. We'll split this output into mean and log var, right? And then we'll return the mean and log var simply, right? And then we will function reparameterize, all right, in which we'll be having taking mean and log var again, and we'll be calculating a random array epsilon just to make sure that we generate a new latent vector. We'll be using this, right? We'll be generating a new like random vector. We're going to multiply that by the exponential of log var into 0.5, and we're going to add the mean just to make sure we'll get a new latent vector, but in the same latent dimension, right? And then let's build a decode function only for this sample function, only to use it in the sample function. We're going to have z, which is going to be the latent vector, right? We're going to have another parameter which specifies whether you want to use sigmoid or not, and then we'll pass this z to the decoder, right? If apply sigmoid is true, we're going to apply sigmoid, return probabilities, else we'll just return the logics, right? And then we'll build an optimizer. We'll specify the optimizer with learning rate and other parameters. And this is our loss function, log number PDF, and we'll just use this to actually create a loss function here. We'll just call the encoder, we'll reparameterize decoder, we'll perform the sigmoid, we'll be going to calculate the gradients and all that, and then we'll just find the loss function. Again, we're going to do the same thing just like we did before, right? And then this is like each step, what is happening like in each training step. As you can see here, same thing. We have gone through the same thing. We have gone through the same thing in the last video also. We'll be creating each training step, in which when we are training, we are going to call this function multiple number of times, or we'll be just looping them, right? And then again, same thing. I'm going to first create the encoder. I'm going to call the encoder on X on the input data. We're going to perform reparameterize decoder, again sigmoid, reduce sum, calculate the loss function, and then we are going to here update our gradient, update the gradients or train the model. And same here, we'll be generating a random vector for generation for the input, and we're going to pass this latent dimension to the CVAE to actually get this audio output. And then sorry for this, probably that is not generate same images, this audio, or yeah, audio images or something. And then in this generate and save audio, we'll use it to actually create checkpoints, right? To actually generate it at like each training step, maybe, right? We'll be calling the encoder, reparameterize sample, not decoder. And then because this is inference time, right? We'll be using the sample function. And then so this is a training loop in which we'll have a we'll have a for loop. We'll be looping through the training data set, right? We'll be taking its like data, and and then we're going to perform the model train step. We'll be performing the model, or we're going to perform the train step, and then we're going to do the same for test data, right? To actually compute the loss, like not for updating, because the goal of test data is not actually for training, right? And then we can actually print the results, these scores, and then we'll build the final function, generate and save images to actually generate the images of audio data. And you can actually run it. I think I'll just run it and we'll just wait for a moment. Maybe I'll pause the video for some time. I think I'll run it. So I just started running it. So yeah, I'll see you after training. So yeah, the training just started. Then It might take some time, but you know, we'll just wait for it. All right. So okay, I'll pause it for now. I'll probably wait for some time, maybe 10 minutes, and see you back. I mean, if the training is taking a lot of time, I'll probably I'll probably leave it for you to actually take your time. All right. Right. I'm going to pause the video. I mean, yeah, it is taking a lot of time. So, you know, I'm going to leave it here. I'm going to leave it here for you. I think it is time for you to actually run the model. Wait for yourself. I think it is not healthy for my computer also to actually keep it running and recording. So yeah, that's it. That's it for this video, and I'll see you in the next video. And then I think we have ended various slot encoders. Again, we'll come back to all of the topics. Don't worry, like we are not going to leave language modeling from uh, like completely. We'll be coming through we'll coming back to all of these topics once I have covered the basics. We are just covering the basics now also. There is like a lot of things that we have to do in each field. So we'll come back to various not encoders and other models too. But I think for now we're going to go to stable diffusion. It is going to be very exciting. Like it is stable diffusion is also very like mind blowing, yeah, technology, mind blowing models. And I think we'll be learning about stable diffusion. It is actually pretty similar to GANs, but we'll cover all of that. All right. So thank you for watching. I'll see you in the next video. So yeah.